And now, is there the sound? Yeah, I can see my microphone. Great. Okay, so as usually, for those who are in Zoom, feel free to write in the chat. For those who are offline, just stop me if you do not understand anything. Okay, so when we have some easy to optimize functions like the one used for linear regression, then probably we do not need all of these extensions, since we just can use the classic stochastic gradient descent with probably some regularization. But when our function is difficult, we may find out that it will not just converge, it will not find out itself in the local minimum. So we need some extensions, and frankly speaking, there are two groups of gradient extensions methods. So the first group is the one which modifies the update rule, and momentum is one of such methods. So instead of subtracting the anti-gradient of each parameter, we do the following thing. We accumulate the information which we obtained while processing the previous batches, so that if we encounter outliers in the current batch, the direction of a gradient will not move in some other side. So thanks to this accumulation part, we can stay in this trajectory and converge much more quickly. Here you can find some classic values for the hyperparameters. So usually alpha is set to 0.9, so that we have a high influence of the previous gradients. Another method of this group is Nesterov momentum, but again, here, you need to, you want me to explain this formula, right? Okay, so on each step t, our ht will be that very thing which is subtracted from our current parameters. So usually we have like gt, the gradient, on the current step subtracted here, but now it will be ht, and it's defined by the following formula. With coefficient alpha, we add the previous value, like the one which was accumulated during the previous steps. We may use 0 for the very first batch. We can probably use only this part, right? So it will only depend on itself, since it did not see any gradients previously. But starting from the second one, we will use the alpha. By the way, you will find the answer to your question when we get to the Adam, which is optimized especially for this very initialization. Again, we can add this with coefficient 1 minus alpha, so that it will be a classic recurrent dependency. But at the same time, if we multiply by 1 minus alpha or not, this is just a linear transformation. We can just adjust our learning rate so that it embraces this very part 1 minus alpha. So now clear, yeah, can move forward. So the Nesterov momentum is considered to be a more advanced method than momentum, but it requires a bit more calculations. And again, my goal now is to show you methods which are currently used, and not give an overview of all the theoretical methods. If you find it interesting for yourself, you can inspect this one as well. I will not stop here for the moment, and we will not encounter it in the course anymore. And the second group of methods are the ones which optimize the learning step, the learning rate, and make it element-wise. So each element of our neural network will have its own learning rate. And the first method in such group is AdaGrad. So the learning rate for each parameter, which parameter g, is calculated by the following formula. So instead of just multiplying by the common learning rate for our neural network, we also divide it by this part. This part G capital is the one which accumulates the information of the square gradients of the parameters. The idea is very simple. So if our parameter had high gradients and had high gradients throughout like long period of time, probably it has already converged. So like if it was modified a lot, now we need to modify it slightly less, yeah, so that we can accumulate the information about how much it was changed and divide its learning rate by this very value. But the main drawback, the main shortcoming of such a method is that it only accumulates this one. G capital is the part, like it's the adjust coefficient for the learning rate of the parameter. So that's how the parameter G is updated on each step. We take the previous value, we subtract the gradient, like in classic stochastic gradient descent, we would subtract GT multiplied by nu t, right, eta t. And now we also divide by this very part, which accumulates the information about the square gradients of this parameter. Because it doesn't matter whether your gradient was 5 or it was -5, right? It means that anyway, it was changed significantly and like much more significant than the one with the value 1. So we use the square value to show the magnitude of the gradient for these parameters throughout the previous steps. But the drawback is as follows: we only add on each step, so no subtraction is done, and moreover, since here is the square, we only add positive values. So throughout the time, it only accumulates information. It does not become small. And what we can find in practice is that our parameter was moving a lot, then it needs just to like adjust a bit, and then it again needs to move for some time. And other graph will be a bad solution for such cases. So there is a method called RMS prop, which was invented especially for such cases. So the only difference with other grad is that we add this momentum style to the previous formula. So previously it was just accumulating, and now it's with coefficient alpha, so that when after some like large amount of steps, it was not changed a lot, the gradient was very low, this part can restore, it can like again become a small value, so that our parameter will be changed significantly. So that's the idea of RMS props, use the momentum style for updating the learning rate for each parameter. That's it. No questions? Can move forward. Okay, so the last method which we will take now, and that's I would say this the universal method for neural networks. So up to now, to my knowledge, in all the spheres of deep learning, Adam is used as like the optimal method for optimization.
It's preferred to use GT with momentum.
Well, to my knowledge,
even vision transformers are usually trained with SGT with momentum. It's only in natural language processing that
Adam was not used in natural language processing up to 2020.
Nowadays it's like universal.
Yes, but vision transformers are using the transformers library by default, and it was only like half a year ago when they allowed to use your custom optimizer. It was, of course, you could do this, but it would take a while.
Anyway, you don't use Adam usually, neither for fine-tuning or threatening.
Well,
it's correct to say that it's universal.
I will not argue now, but well, again,
I can refer to articles.
Okay, so like if you are sure in your words, okay, but again, from what I know from like some basic structures of PyTorch, etc., they suggested using Adam as the first method, since it does not require you to tune any parameters. And the idea here is as follows: we just combine the momentum and the RMS problem. So here is the part for momentum, here is the part for RMS problem. So first of all, we verify the update rule, and second, we make the learning rate element wise for each of the parameters. What's the difference between like these implementations, which we saw a couple of minutes ago? We can see this very part divided by 1 minus beta 1, 1 divided by beta 2. The idea is, again, quite simple. So since we were starting with the 0 value, since on the first iteration, our previous value was equal to 0, we need to scale with respect to the weight of the 0 value. So some usual values are beta 1 is about 0.9 and beta 2 is 0.999 if memory serves, or probably vice versa. It doesn't matter, so you do not have to tune these parameters in practice. But the idea is to scale with respect to the weight of this 0 value. So after scaling, we get an unbiased estimation, and that's the update rule. So that's the Adam, and like, I don't know if it will be spoken here about Adam V is like its small extension when we add the weight decay, which we spoke about last lecture. So this L2 regularization, so-called, which is slightly different, right? So adding this to Adam will get us to Adam V method, which is like used as a default methods in most libraries. That's it. So if there are any questions regarding the optimization, let's stop here. If no questions, okay, let's move on to the second lecture. So the topics for the lecture is follows. First of all, we need to have an overview of so-called special layers, which are different from linear functions or observation functions. And we'll speak about the weight initialization and why this is important in neural networks. A disclaimer: when you do not initialize your network properly, it can simply not converge, and you will find like the performance much worse than the simple linear regression. And the feature importance, we'll see a simple yet effective method for calculating the feature importances in neural networks. So you probably know in linear regression, we need to scale the features and we can inspect their weights. The same for logistic regression. In gradient boosting, there are again some permutation-based method, but it becomes harder to estimate the feature importance. And the same idea holds for neural networks. So the first layer, which we'll now see, is the dropout layer. The idea is as follows. A couple of years ago, it was found out that when neural networks overfit, we can find so-called coadaptation problem of neurons of adjacent layers. What does it mean? The layer from the neurons from the first layer, they do not try to approximate the value. They like think that the neurons from the next layer will correct their biases. And so after updating the gradients, they rely on these neurons from the next layer. And as a result, it leads us to overfitting, the worst problem, right, in machine learning. So to prevent the problem of coadaptation between neurons from neighboring layers, let's randomly zero a part of them during training. So what does it mean? That's the classic neural networks. Like we had 3 input features, then we have the first layer of shape 3 by 2, then we have the next layer of shape 2 by 3, right? So we like multiply going from neurons from one layer to another. And the idea is to randomly exclude some of the neurons during training. On each training step, new random neurons are excluded. That's it. So it will, how will it tackle the problem of coadaptation? Of course, since this neuron is now disabled, it cannot correct the errors from this layer, right? As a result, these neurons cannot rely on this, since if they do, they will have like very large gradients at the end. So we randomly exclude some of them. Here is the formal definition of how to apply a dropout. So it's applied for each layer, like for one layer in Torch, in Keras, I don't know. What should not be done? The dropout should not be applied, first of all, to the input layer. Second, to the output layer. Why? Because if we apply it to an input layer, it will randomly zero some of our features and we will lose some information, right? Our network on this step will simply not see this information. If we apply it to the output layer, well, it will zero the result of our network. That's again not correct. It will not tackle the problem of adaptation. It will simply lead us to awful results. So here are some other peculiarities of the dropout. So used to prevent the overfitting. Some important notes. Do not forget to rescale the output. What does it mean? Let's go back a bit to our image. So on this layer, we previously had two neurons, right? If one of them is randomly excluded, let's think about this value. I will now use the desk. I think like here. So we had two neurons, let them be like Z1, Z2. And each of the neurons from this layer, let them be like, I don't know, X1, X2, X3. They depended on this one. So X1 was Z1 multiplied by some weight plus Z2 multiplied by some weight, A, and probably some bias, right? And now, since we zeroed this very neuron, it's like only this. Problem is, if we do not rescale, if we like omit this part, the variance will be decreased. So if previously the variance was something like, I don't know, let them be some value A, now it will be about A by 2 or A by 4. I do not remember exactly. It's not so important. So the on average, it will be decreased. And again, if we had some positive values here, the value will be again decreased. And that's the problem. So in order not to have like the decreased order of our values, we need to rescale the output from this layer. So now when we calculate each of these neurons, we rescale them by 1 minus probability of zeroing from this layer. So now it will be like Z2 multiplied by the 2 divided by 1 minus B. That's the important issue about dropout, but if you are using some classic frameworks like Torch, you do not have to take care of this since Torch does it itself. The next peculiarity of the dropout, okay, some default values. If you don't know which value to start, use 0.2. It's like usually this one is used, but of course it depends on the task. Sometimes it will 0.5, sometimes 0.1. The idea is that values larger than 0.5 are very rarely used, again because like it will zero too much information from this layer. It does not contain learnable parameters since it only performs some operation of zeroing the neurons, and it only has one hyperparameter, that's P, the probability of zeroing neurons from the current layer. On inference, right, we do not need to zero values. We want to use as much information from our neural network as possible, because if we do the zeroing operation, it will lead us to stochastic results, probably a bit worse results, and that's not what we want our network on the inference part, so while we are predicting. So on inference, we need to disable the dropout, so no rescaling will be done, no neurons will be zeroed. To do this in Torch, we need to call this very command model eval. And the last nice peculiarity of the dropout is that sometimes we will not disable it during inference when we want to get some uncertainty estimations. So one of the state-of-the-art methods for gauging the uncertainty estimation of our neural network is to enable the dropout on inference, make some case stochastic runs through our network, let it be like 10 stochastic runs, and then average the results or see the variance of the results or calculate some other statistics from this number of stochastic runs. It can give us a good proxy for the for how certain the neural network is in its result. But we'll speak much more about this in lecture 6.
Question.
Yeah, sure.
And could you please explain more precisely why overfitting happens in real life?
Why it happens?
Yeah, why overfitting?
So overfitting happens in all the models of machine learning, be it a linear regression.
No, I know. I mean, can you please again explain why? I mean,
Why dropout helps to tackle the problem? Yeah, sure. So what's the problem of co-adaptate of neurons co-adaptation? While training, the gradient for these parameters depends on these parameters. The gradient of these parameters depends on these ones, right? And when we have a lot of parameters in our neural networks and not too much data, what happens very often? So the neurons from this layer, they think, okay, I will not try to approximate the target value. I will not like correct my errors, since I know that the neurons from the next layer will do it for me. Neurons from this layer think, okay, I will not adjust the value too much because the neurons from this layer can do all the job for me, and that's it. So they co-adapt, and their values are very much dependent on each other. And when we enable the dropout, we randomly exclude them on each training step. So like the first batch, 16 elements, we pass through the networks. The network looks like this. The next step, probably like this is okay, but this one is zeroed, and probably this one is zeroed. Again, the neurons from the previous layers, they see, okay, I cannot depend on it since it can be zeroed, and all this information like will be lost. So that's how the dropout tackles the adaptation. Hope it helps. Any other questions on this, on the dropout? Okay, so let's continue. And we will not stay here for much, but it's nice to know another method called drop connect. First of all, I'll say that it's used much more rarely than the dropout. It's used only for some special implementations, but anyway, the idea is simple, and probably it's better that you know this. So what we do in dropout, we randomly zero some of the neurons. I hope you will see this. So we can see this layer I, this is the next layer, right? And what we can see in dropout, we zero one of these values. Left here it's this one. So it is not connected with any of the previous neurons. You see these arrows, they are like unconnected here. These two are okay. And in drop connect says a bit different thing. So instead of zeroing the whole neuron, like the whole synapses, the whole weight coming from this neuron, let's do another thing. Let's simply zero some of the weights of our matrix. Again, with some probability p, again, it will change on each training step, but like the idea is very close. Again, we need to prevent the problem of adaptation, but here they say like, and if we zero the whole neuron, probably it's not great since we lose like the whole place where we could store some info, and let's instead zero some of the weights. But again, it was shown to be a bit worse. There is, by the way, another method, max out. I encountered it only once in my practice. It says the following thing: each neuron from here goes from neuron here, right? Like they are connected to synapses. Max out says the following thing: take only the one with the largest weight. So here is the largest weight. And then do this one, and this one, and all the other will be zero. It can significantly reduce the number of parameters to tune, the complexity, the time that neural network works, but it will be much less expressive since it's like these and these neurons, they will be like stripped out from a network. They will not be used in the future. That's it. So any questions regarding these three methods? Okay. So one of the most vague topics of deep learning is the batch normalization. It's vague since each year there is a lot of research on batch norm, and each year the conclusion of this research differs from the one which we saw previous year. So what's first of all the batch normalization? Here is our input matrix. Let it be the 2D for like tabular data. So we have some m samples, and each of them has some n features. That's it. The first step is to calculate the mean and the standard deviation for each of the feature in the batch. So we calculate the mean and standard deviation of this column, of this column, of this column, etc. We get the statistics. The second step is to normalize. From each feature value, we subtract the mean of this feature value in this batch and divide it by the standard deviation. So for like better comprehension, the elements in the batch now depend on each other. So since we calculate the mean and the standard deviation of feature with respect to the batch, of course, each element in the batch now becomes dependent on another element. Probably that's the first time you see in machine learning such dependency. After we normalized each feature, subtracted its mean divided by the standard deviation, we make the reverse operation. We add some, we scale and shift. So we multiply by some like learnable value for this feature and add again some learnable value for this feature. So that's the output of batch norm. Again, what's the idea? Some values in our batch can be outliers, some can be very small, some can be very large. And the idea is to prevent meeting these outlier values in the following layers of our neural network. So we normalize, and then we do some scale and shift, like reverse operation, so that it can learn something to make some shifts. That's it. That's the batch norm. But okay, so that's the formal algorithm. If you need me to explain in some more detail some training phase, like that's how batch norm works on training. That's it. On inference, it will be slightly different. If everything clear here, okay, let's move to the inference step. So you can see also this part. We have not spoken about this. Here is probably a bit easier for someone explanation of the batch norm. And let's speak a bit more about this part. So again, on training will depend on the elements in the batch, but it's not a good idea to have our elements dependent on the batch during the inference phase. So on inference, we just want to have the result of a neural network. And if it depends on the batch, like whether we have one element or 10 elements and which are these elements in the batch, on inference, that's not a great idea. So instead of calculating the batch mean and standard deviation statistics for each feature, we do the following trick. During training, we accumulate the statistics for each feature. So during training, apart from this like algorithm, we also accumulate the mean and the standard deviation for each feature. And again, we do it in the momentum style. We do it like in a recurrent style. The value for alpha is usually set to 0.99, so that it's not biased towards any batch. And again, we probably start with the like initial value, the one which was for the first batch, and then we continue accumulating this information so that by the end of the training, our statistics are quite unbiased towards our training set. They have this mean value for our feature and the standard deviation for each of our features, I would say rather precise. So that's for the inference phase. And instead of calculating the mean statistics, we use this accumulated moving average mu and sigma. again, after this, we do the scale and shift operation. And what's important to understand now that these parameters used for scale and shifting of each feature, they are learnable. They are learnable for each feature separately. So the total number of parameters in a batch norm layer is like how many gammas we have, the same as the number of features. How many betas we have, the same as the number of features. So the total number of parameters is 2 multiplied by the number of features. That's the batch norm. Batch norm possesses a lot of benefits. Some of them are arguable since it is not proved that it exactly like enhances some processes. But anyway, let's have an overview of them. First of all, since we mostly use the asymmetric activation functions, so-called ReLU-based, right? Again, for those who forgot, ReLU is having 0 value for all whose argument is less than 0, and x equals to x when it's larger than 0. Of course, this one is asymmetric, and all the modifications, Jello, Elo, etc., they are all asymmetric. The result is that these activations, they lead to enormous number of positive values, right? These positive values can, like, here are the 2 problems which follow from a large amount of positive values. So first of all, the scalar products of vectors of different objects will be very high. Okay. So what does this mean? If 2 elements are completely different, their scalar products will anyway be very similar. They will be high because we have a lot of positive values, and multiplying y positive value by another will again result in a positive value. And the second, probably much more important problem is that the gradients of larger parameters. Larger parameters, again, we cannot say that one parameter corresponds to exactly one feature, right? But anyway, this is what happens in neural networks. Some parameters tend to pay more attention to some features, and the gradients of larger parameters will dominate the update rule. So our training will be biased towards updating the values of these large parameters instead of some others. And that's the problem when we have a lot of positive values. Batch norm surely alleviates this problem since it renormalizes the data, and the data distribution becomes symmetric. That's it. The next point is that many modern architectures use skip connections. Skip connection is a topic which we'll cover on our next lecture, probably on lecture 4. And its idea is very simple. So we have some value x, and after we make some transformations, let it be some layers, some again batch norm, dropout, etc. layers. We have some output x with head, and instead of using only this value, what we do is we add it to value x. So that's the skip connection. Instead of modifying our data, just tune the existing value with the modified one. It's used in like all the modern NLP architectures, all the transform-based architectures, for a lot of computer vision and speech recognition architectures like ResNet. And batch norm allows to, again, alleviate the, not to alleviate, but it works very well in conjunction with skip connections, since it normalizes the activation norm and allows to skip connection not to have large values. So if we would not have batch norm, after modifying and each time adding some value, we'll find ourselves with some probably large values, or at least with large variance of our values. And now using the batch norm, this will not happen. It also enhances the smoothness of the loss landscape, so it makes it much more smoother, which allows us to use larger learning rates. And larger learning rates means that we can converge much faster, we can spend less time on our training. And another peculiarity, but this one is arguable, since there are research which shows that Yes, batch norm works as a regularizer and helps us to deal with overfitting, but at the same time, there is a contradictory research which shows no, batch norm does not help to deal with overfitting. It's only dropout and some other some other things from neural networks that help to overfit. But anyway, like this one is arguable. Some tend to believe this, some have an opposite point of view. Yeah, first of all, if there are any questions regarding the procedure of batch norm or the peculiarities, let's discuss them. Okay, no questions. Moving forward, so the peculiarities of the batch normalization. Oops, pardon. As we've discussed on training, the result for each element depends on each other element in the batch, since we calculate the mean and standard deviation for each feature in the batch. The second is obvious. Large batch sizes provide more precise and batch statistics. Well, that's, I guess, easy for everyone, since the more elements we have, the more precise the statistics are. The learnable parameters, it has gamma and beta for each feature. So totally 2 multiplied by the number of features. It has 2 hyperparameters, but in practice, they are never tuned. So the first one is alpha for statistics accumulation, right, for applying it on the infinite space. And another one is epsilon for scaling. So in case the standard deviation is like 0, all the elements in the batch have the same value, and it's applied, I don't know, after immediately the first input layer. This, oops, pardon, it's for inference. This one, sigma E, can be 0 or can be very, very small for some values. So it's usually tuned, like a very small epsilon is added to prevent the non-values here.
Why do you use learnable parameters? Why just go to simple scale?
The problem with simple scaling is that every time we will move back to this order from like when we subtract the mean and divide by the standard deviation, the mean of such distribution is 0, the standard deviation is 1, since we divided. Yeah, and if we only stop here, only stop on this scaling operation, it will each time it will reduce our order. So if we need some larger values, for instance, for classification tasks, well, because applying softmax with values 0 and 1 will give probabilities about 67 and 0.33, if memory serves, something like this. And if we want our values to be larger, the batch norm will simply prevent us from doing this, and that's not great. Since it like reduced the total scale usually, and then it moved us to some other distribution, which is helpful for the neural network. That's it.
So it's just like press scale.
Yeah. And this, again, already discussed, during training accumulates, during inference, it uses these accumulated statistics. If there are any questions on batch norm, let's stop. If there are no questions, let's move to another type of normalization used mostly in NLP. So watch, here are some types of normalization. Let's, we will not use these ones in our course. Batch norm, delay norm, what they do? Batch norm takes elements from the batch, right, and normalizes them with respect to each other element. And what layer norm says, it says, well, it's not great that first of all, I use the other elements in the batch. So like my training is dependent on which elements are in this batch. And second of all, there are some structures of data when we mostly need to scale, not with respect to the full batch, but with respect to element, with respect to how to say, oh, that's not feature wise. Okay, let me show this on the desk. So for an NLP task, Again, of course, it can be also used in computer vision. It can also be used like for speech recognition. But in NLP, the visualization will be the most the easiest one. So, what is one element for NLP? One element is usually one text. One text consists of the number of words, or let them call tokens, right? So, and what's one token? We will cover all of these topics a bit later, but for now, one token of one word is represented by one vector of fixed length. Let it be the vector of one word. So the text has a number of tokens of words. So one text is a 2D tensor. It's one text. And in the batch, we have several texts. So this input tensor is 3D, like 3 dimensions. The batch size, the number of words in each text. For now, for simplicity, let's assume that each of the texts in the batch have the same number of words. Let it be this way. Each word is represented by the vector. So yes, probably we can rescale, like let this be the first element. I hope it's visible for those who are in Zoom. Let this be the second text. Of course, what we can do, we can normalize like the first, the vector corresponding to the first word with respect to all the first words from the text in our batch. But like the logic is slightly broken here. What's much easier to be done is to normalize each word in each text with respect to other words in this text, right? Because that makes much more sense. So we will normalize values inside this batch with respect to them. So like word 1, word 2, etc. And what we do for each element in the batch independently, we calculate again the mean statistics for each feature and do absolutely the same operation. We first scale and then we rescale back using some learnable parameters. So this text, it only like the normalizing values, they only depend on itself. It does not incorporate any other texts. This text only depends on itself, etc. So that's what's laying on. And first of all, it can be only applied for 3 or more tensors, since for 2D tensors, it will like coincide, or it will be the same as batch norm. And another like main probably peculiarity that it's now not dependent on the elements in the batch, it only depends on the vectors of words from itself. So we do not need to accumulate statistics during training, right? Because like on both on training, on internet, it is not dependent on other elements. The learnable parameters are absolutely the same since we do the same rescaling operation. And the hyperparameters is now only epsilon for scaling. We do not have this alpha for statistics accumulation. That's what laying on is. If there are any questions of this, please ask. No questions. Okay. Some notes. So lane normalization is mostly used in transformers architecture. This is the ubiquitous architecture for NLP tasks. So it leads to state-of-the-art results for like 99% of NLP tasks. And it's also used in computer vision, the vision transformers. It was a model called there were some models which showed some state-of-the-art results on some computer vision benchmarks. It was something like ZERT, probably called, not remember exactly. And of course, some of them are used for speech recognition as well. This architecture, it uses delay normalization since each of the elements in the batch depend on the number of vectors and they are rescaled with respect to each other. But apart from transform architecture, batch norm is used much more often. So for tabular data, batch norm usually leads to better results. That's it. So some notes on the order of the layers. frankly speaking, there is no theory behind this order. So, like, why batch norm is used here before activation? No one knows. So, like, it was used this way in the original paper where the batch norm was suggested, and like some researchers tried to use it after, but it led to worse results. So these are some conventional order of the layers. First of all, we do the linear transformation. Then we do the batch normalization operation. We rescale the output of our matrix. Thanks to it, we make the activation, and we apply the activation function, and we use the dropout. In some of the research, the authors suggested using the dropout after the linear layer, since they believe that it deals with overfitting a bit more, a bit better. But this modification is used much. The dropout is now used not after the activation. The difference in results in theory.
The same outputs.
No, of course not. So let it be this one. We have some values, we rescale them, and we have some distribution, let it be with mu m for each feature and standard deviation sigma for each feature. After applying the activation, we have, like, let it be value, we have only positive values, since this function is asymmetric. Have only positive values, and after dropout, we will also have only positive values. But for this modification, we'll first apply linear dropout activation. Here we have only positive values, and after normalization, we are not sure that we only have the positive values, since we do the rescaling operations. And it can be like the mean can be even below 0, or the, you see this. So, okay, let's move forward. And now the weight initialization topic. So let's initialize the weights properly. Probably the first idea which comes to your mind is to use some constant values, some low ones like zeros or ones. But what's the problem of initializing with constant values? The problem is that if we let it be, we initialize all the neural network with ones. The same gradients for different parameters will have the same values. What do I mean? Let's use all this once again. Let us have 2 input features and 3 neurons on the first layer, so that the first linear transformation is of shape 2 by 3, right? So we have 2 features, x1, x2, and we have 1, 2, 1, 2, 1, 3, 2. That's it. So after applying this linear transformation, we'll have 3 neurons: Z1, Z2, Z3. Is it visible? Okay. So if we initialize all of them with ones, Z1 is equal to x1 plus x2. Z2 is equal to x1 plus x2. Z3 is equal to x1 plus x2. Well, surely we have some biases here as well. We can use like plus b1, plus b2, plus b3. But again, if they initialize with the same values, these are all the same values. So they are not different from each other. After moving to the next layer and calculating the gradient during the backpropagation, we'll have the same update rules for them, since they depend on like the same values, right? So after using the gradient descent, we will have the same values. And if we continue the training, if they after initialization use absolutely the same values, after like any number of steps, they will anyway have the same values. So they will not differ from each other. So the problem is that a very large number of parameters in our neural network will do the same job. They will be absolutely the same. That's the problem of initializing the weights with some constant values. Any questions? Okay. So the next idea is to initialize them randomly from some distributions, probably some standard distributions like standard normal or standard uniform, with some fixed standard deviation. Let it be like the ones which can see on the slide. What's the problem? Since we use the fixed standard deviation, we simply do not care of variance and sometimes of the mean. But for these values, we take care of the mean, it's okay, but we do not take care of the variance. So as a result, especially on the first steps of training, we may find like our neural network may output very large numbers. That's the problem. If it outputs very large numbers, significantly larger than the target value, it will lead to very large gradients. Have large gradients, we can simply move away from our local minima. Instead of like gradually moving to the local minima, it will have very large updates, and the convergence is surely not guaranteed in such a case. That's the problem if we initialize with some large value, like with the values which are large for our neural network. If we're vice versa, initialize with values which are too small for our neural networks, our gradients will be vanished, so they will be too small, and as a result, again, will not converge to the local minima. And this problem, it truly aggravates with depth increase. So if we have one layer, then okay, that's probably okay. If we have 10 layers, the variance on the last layer will have some very large values. I don't know, like probably 15, 20, and if our output is especially rescaled, it will lead to very large gradients. That's the problem with fixed standard deviation. So a couple of methods were suggested recently. First of all, this group of methods, you can see that in brackets I put here Glorot and Akim. The problem is that the first person who suggested such initialization was the person Javier Glorot. That's his name, that's his surname. And he wrote this paper in conjunction with Joshua Benjo, and several years later, the author He, they suggested some modification for the normal, like for this very thing. They thought that this one works better than this one. That's about the names of them. Now the values. So this gain, in majority of cases, it's taken equal to 1. So we can just omit this. In this formula, for some special cases, when instead of like for some special layers, for some attention layers, it may output, it may change a bit, but for now, let it be simply 1. They suggested the following idea. Let's make the standard deviation dependent on the number of input features and the number of output features. We make it dependent on both of them, since, oops, I made a mistake here on the slide, I'm sorry. Non-rule. This group of methods, it was invented for hyperbolic tangents, sigmoid, and logistic functions. Yeah, I probably copied info. So, I'm sorry. Here, for some symmetric functions like hyperbolic tangents, sigmoid, and for them, of course, in the symmetric, we need to know the number of input and the output features as well. But for some asymmetric functions like ReLU and its modification, we do not need to know the number of output features. So several years later, came in that was probably the surname of the author. He suggested a modification where we are only dependent on the number of input features, and again, both the normal and the uniform distribution. So for removing these modifications, it was theoretically proved that this one provides much better values. And for sigmoid, hyperbolic tangents, softmax, logistic functions, it was theoretically again proved that this one provides the optimal values. For the, I mean the optimal values for the first iterations when our values are still not tuned. In Torch, the value is initialized closely to here, but instead of 3, we're using simply 1. There is some logic behind this, but it again differs like theoretically, to my knowledge, it does not matter which ones you use, but like the Doge decided to use one here, and they used it both for initializing the weights and the biases. The question which probably might have arisen is what's the difference between the normal and the uniform? The answer is simple. There is theoretically no difference. So both of them are proved to be optimal for these activation functions. And it's just a matter of preference. Some prefer normal, some prefer uniform. There was some research about 5 years ago on some benchmarks where they tried to use each of them and compare them. And it turned out that for those very tasks, the uniform distribution provides some slightly better results, but like it does not mean that this one is better. It's just more the matter of preference. That's it. So I guess we are over with weights initialization. If you have any questions. Okay.
The other distributions. Only from normal.
And which ones would you use? Well, of course, there are some like symmetric distributions, but I cannot even like quickly resemble any of them. Like the beta distribution is not symmetric, the alpha, the gamma distribution is not symmetric, the truncated model again not symmetric. And the problem is that if we scale our inputs, right, in our target values, we usually use this standardization operation. It's symmetric, so probably we need, as a result, also to have some symmetric values. So mostly these two are used. Okay, so the final thing which we will embrace today is the feature importance algorithm. How to calculate the feature importance for neural networks. Oops, that's it. Surprisingly, this algorithm was suggested not long ago, just 4 years ago, but it's very simple and it does not require us to fit our model several times. The algorithm is as follows. We first have some trained model F, we have some feature matrix X, target vector Y, and error metric L. So since we consider this to be an error function, the lower the value, the better the results, right? So of course, instead of this, we can use some quality function and the larger value for them would signify better results. What's the feature matrix X and target vector Y? So for now, let's assume it's either the training set or the validation set. For now, we do not care about this. So the algorithm is as follows. First of all, take our train model and estimate the error of this original model on our target vector. Let it be, you can assume now, like mean squared error, for example. The next, what we do for each feature in our data set, we generate the matrix X perm by permuting feature J in the data X. So what we do, we only take this feature column and we randomly shuffle the values from it. That's it. So what it does, it surely will break some connection between this feature and the true outcome. What we do next is we simply estimate the error with the result of our model for this very permuted data set and the target vector. So instead of y large, we have y. You see, right? If we want to have as precise results as possible, repeat these two steps for some number like k steps and average the results. That's it. So then what we do next is we calculate the permutation feature importance as like either dividing our permuted error by the original error or simply subtracting one from another. So for our case, since we're using an error measure and the smaller the values, the better, what we, if here we find a positive value, it means that the feature is like totally useless. So after excluding, let it be like this feature, we have better result. I'm sorry, vice versa. So after, if this value is positive and is large, it means that the feature has a very high importance since we excluded this feature and our error surged significantly. Again, if this value is small or if it's even below 0, it means that the feature does not have any influence usually. Of course, this algorithm is just a very rough proxy. So it doesn't mean that if like after using this algorithm, we can totally rely on its results. No, but in most cases, it gives us a rather precise overview on which features are important, which ones are not. Yeah, I forgot to explain this. So after calculating this Fij value for each feature, we sort the values in the descending order. So the feature which has the largest value here is considered to be the most important.
What does previous feature mean? You remove the value of this feature between instances?
Yeah, exactly. So let us have this feature matrix. Let us have feature J. So it had some values like 0, 2, -1, 0, 5. Let it be this way. After permuting, we'll have absolutely the same matrix except for this feature. It will be something like -1, 0, 5, 0, 2. So we simply permute it.
I wonder how you use it like in practical case, because if you take an image and produce just one pixel, it will not change anything at all. Or you use it for words, like do you like change the second word in each instance, in each sentence? It's certainly not applicable for computer vision, right?
It's totally not applicable neither for computer vision, nor for NLP, nor for speech recognition. And for NLP, what do you mean the inference of one feature of one word?
Okay, like in images, each pixel is a feature.
Yeah.
If you shuffle just one pixel.
No. So look, in computer vision, it's very hard to estimate the importance of one input pixel. Yes, surely we cannot do this. There are some other algorithms for
No,
this.
where can you use this?
For tabular data. So you have a lot of features. You need to know which ones are important, which ones are not. For tabular data, that's the best application. Probably not for tabular data.
You don't use neural networks for tabular data. You usually don't do that.
On Kaggle, on the majority of last competitions, we use neural networks in conjunction with gradient boosting and other algorithms.
Anyway, it's kind of strange.
No.
It's applicable in very few algorithms. You usually don't use it. You're not for tabular data.
Well, I would say we use a lot of times neural networks for tabular data, and mostly we use it like we very much use this algorithm called the conditioning the results of one model on another from machine learning determinants. Anyone remembers? The stacking. Yeah, so the stacking, what it is, we use several models, and another model will take their outputs as the features, process it, and use the final value, like a teacher who gathers the results of the students and provides some output. And for such cases, again, we can enlight which of the models provide valuable results, which ones provide not valuable results. And again, for cases when we care a lot about quality, I will not say about Kaggle, since this is not exactly the practical case, but for some cases we take care a lot about quality, and again we can find out which models in our ensemble are important, which ones are not. So, well, I would say this algorithm is used a lot, and of course for some applications like computer vision, natural language processing, speech recognition, we would not need this because it's hard to estimate like the importance of one feature of one word, but it's used in a lot of other applications. And another important notice about this algorithm. So I first told you that it doesn't matter which split we used, like X and Y. Did they belong to training data or to validation data? But in fact, these matters, and this is the code from sklearn docs. The idea is that, frankly speaking, you can use this algorithm on both the training and the evaluation set, and it will show us some decent proxy for which features are important and which ones are not. But we can also use this algorithm to detect the features which lead our models to overfitting. And we can do the following thing. We can calculate this on some held out set and highlight some important and not features. And at the same time, we can do this on the training set. The features which have high importance on the training set, but not on the validation, on the evaluation set, they might cause our model to overfit, since like they do not enhance the generalization capability of a network. So that's how this algorithm can also be used for detecting features which help our model to overfit. So that's it, and just a small summary of our lecture. The dropout, we use it to tackle the overfitting problem, batch norm or layer norm for making the training stable, usually much faster. By the way, one fine note is about batch norm or layer norm. When using them, we can not take care about standardization and scaling our data before feeding into our neural network, because the scaling operation is done naturally in this layers. That's it. So the optimal choice of the layers is as follows. Weights should be initialized, first of all, randomly, and secondly, the standard deviation of our distribution should be tuned with respect to the number of features, either from the previous layer or from the second layer as well. And the feature importance can be calculated via permutation feature importance algorithm, the one which we had a look at now, and it can also be used to detect features which cause our model to overfit. So that's it for today. If there are any questions? Okay, so that's it for now. Thank you.